In this video, we'll do a quick dive on vector stores or vector databases or vector embeddings. If you've ever heard of the term embeddings or word embeddings or wondered what that section on OpenAI's website labeled embeddings is all about, then this video is for you. If you've never heard of vector stores or vector embeddings, then that's okay because you've probably interacted with them without even knowing it. Some common consumer-facing applications powered by vector stores would be, for example, 1. Anomaly detection related to your bank account. 2. Recommendations for content on streaming platforms. 3. Automated content moderation on social media. There are only 2 things you need to understand in order to follow along with this video. The first thing is you need to understand what a vector is. The second thing is you need to understand what a dot product is. A vector is a multi-dimensional value. This is in contrast to a one-dimensional value, which is sometimes referred to as a scalar. If you were to ask me, what's my age again? I might say 33, and that would be an acceptable response. On the other hand, let's say you asked me, how would you shoot this basketball so that it goes inside the hoop? I might answer and say, I would throw it at this speed, in this direction, and at this angle. You see how there are multiple dimensions associated with the answer to the second question? This is what vectors represent. Vectors are multidimensional values. You can represent many things with vectors. For example, let's represent someone's personality with a vector. We'll use a 4-dimensional vector and make the first number how sociable they are, the second, how talkative they are, the third, how trusting they are, and the fourth, how confident they are. Hopefully you have a good feel of what a vector is. A dot product is a mathematical formula, just like mx plus b equals y or a squared plus b squared equals c squared, except that it takes 2 vectors and spits out a value that tells you how similar or different the 2 vectors are. The more positive the output of the dot product, the more similar the 2 vectors are considered to be. The more negative the output of the dot product, the more opposite they are considered to be. If the dot product outputs a value of 0, that means that the 2 vectors are orthogonal or unrelated or neither similar nor different. Okay. The rest of this video will consist of 3 parts. Part 1 is a ripoff of Dave Shapiro's video entitled, What the Heck Are Embeddings? And will lay the ground for the subsequent 2 parts. Part 2 is a demo of how to use a vector database, aka a vector store. Shout out to Johnston for the tips and tricks I'll be showing here. And part 3 is a very quick rundown of 2 more advanced concepts related to vector databases. And shout out to Lambert for prompting me to cover these. In this demo, we'll be using Python and an embedding model from OpenAI. ChatGPT and GPT-4 are the OpenAI models most people are very familiar with, but other models offered by OpenAI include DALL-E, which is a model that receives text and spits out images related to said text, Whisper, a model that receives audio and spits out transcriptions of what's being said in the audio, and Text Embedding Ada 002. That's what we'll be using. That's the embedding model that will receive text and spit out a 1536 dimensional vector. I looked into what the dimensions of these output vectors mean, but didn't find anything. If anyone knows, please let me know. I'm guessing the first dimension means how Western or Eastern the source text is. I'm guessing the second dimension means how scientific or unscientific the source text is. I'm guessing the third dimension means how masculine or feminine the source text is. I don't know, I'm speculating. Hopefully that gives a gist of what's happening when a source text is passed through these embedding models and generated or turned into a 1536 dimensional vector. Let's send the text tiger to Text Embedding Ada 002 and see what we get back. Here is the 1536 dimensional vector we were talking about. Now let's send the text cat to Text Embedding Ada 002 and see what we get back. right? Another 1,536 dimensional vector. It's hard to tell these vectors apart, but they are different. Now let's send the text fish to text embedding Ada 002. Right? Another one of these huge vectors. Okay, here is where the dot product comes in. Let's calculate the dot product of vectors 1 and 2, aka tiger and cat, and compare it against the dot product of the vectors 1 and 3, aka tiger and fish. I predict tiger and cat will score higher because they're both of the feline, I don't know if that's the right term, family, right? A tiger and a cat seem to me to be more similar than a tiger and a fish. But let's see what text embedding Ada 002 has to say about that. So according to text embedding Ada 002, tiger and fish are more similar than tiger and cat. Maybe that has something to do with cat being a domesticated animal. I don't know. Let's test out Monday, Tuesday, and Wednesday. Monday and Tuesday are going to score higher than Monday and Wednesday because Monday and Tuesday are closer together temporally, right? Let's see if I'm correct. So in this case, I was correct. Monday and Tuesday scores slightly higher than Monday and Wednesday in similarity. Now you see why these vectors are sometimes referred to as embeddings. It's because the models that generate these vectors embed notions of meaning into them. I couldn't come up with a way of visualizing 1,536 dimensions, but here is a visualization of a collection of three-dimensional vector embeddings. If we look at this region of the vector cloud or vector space, let's see what these points represent. Graph, configuration, filter, graphics, vector, compression. I mean, I guess these are like IT technologies. I don't know. Let's come over here. Let's see what the concepts in this part of the vector space say. Tanker, shortwave, precipitation, runways, GRT, rainfall, maybe like stuff related to like water and military equipment. I don't know. Or let's come over here and see what it says. Minorities, autonomy, republics, provinces, territories, reforms. So this is like political concepts maybe. So that is vector embeddings, word embeddings, the groundwork of vector stores and vector databases. For this demo, we'll take a look at the vector database side of things. Just like SQL tables or SQL databases store uniformly labeled data, and no SQL databases or collections store objects or dictionaries, vector databases store vectors. At the time of recording in 2023, there are many vector databases available on the market. For example, Pinecone or Chroma or Milvus, and all of them are valid. But in this demo, we'll use Chroma simply because it is free. The steps for installing Chroma DB are 1. Clone the Git repository. 2. Build the image in the clone project. If everything works, you should see a Chroma DB server running in your console. 2 common use cases for vector databases or vector stores would be similarity search and anomaly detection. From this list of common consumer-facing applications of vector stores, content moderation on social media would be an example of similarity search. With similarity search, you are comparing vectors that represent user data against vectors that represent concepts defined as unacceptable by a given platform. And when you find the similarity to cross a certain threshold, you will mark the relevant user data for hiding or deletion. Unusual activity associated with your bank account, on the other hand, is an example of anomaly detection and involves generating vectors for all the actions you perform against your bank account and raising a flag whenever a particular vector crosses a certain threshold of dissimilarity. The general technique for how to do similarity search or anomaly detection yourself is outlined here. 1. Break up your data into chunks. The chunks, if your data is text, would commonly be broken up by paragraph, sentence, or word, for example. You'll need to tune the size of the chunks to your use case. 2. Generate an embedding vector for each chunk in your dataset using an embedding model like text embedding ADA 002. 3. Convert your query to a vector using the same embedding model used in step 2. And if you're performing similarity search, you return the chunks associated with the vectors that score the highest in similarity to the query chunk. If you're performing anomaly detection, you compare your query against the vectors for each chunk and raise a flag if the query vector scores below a certain threshold. Let's take a look at this skills matrix. If we search for mobile development, let's see what gets returned. We can see we get matches even though the text mobile development is nowhere to be found on this document. Now let's search for AWS. We can see we get matches of various AWS services even though they're not exactly matching the string we're looking for. If you look closely, you see the top results score lower, and this is inconsistent with what we were seeing before with the dot product. This is because the dot product is one of several formulas for measuring the similarity of two vectors. ChromaDB uses a distance formula instead of the dot product, which is why the higher results are showing with a lower number. The exact matches are showing as 0. A lower score means closer in distance, i.e. higher in similarity, and a score of 0 means your query is identical to the matched chunk. Here's a quick overview of the code behind what we're seeing. On line 56, you see we're breaking things up, i.e. our text, by either spaces or commas. Lines 85 to 88 show us generating the embedding vectors for each chunk. And on lines 96 to 99, we are searching for the top 10 results that match our query. Let's talk about indexing. Indexing involves storing data in a format that speeds up future access or analysis. When dealing with larger data sets, indexing becomes necessary regardless of if your data is stored in an SQL, NoSQL, or vector database. Here's a visualization of a collection of vectors numbering in the tens of thousands, and you can imagine in the case of performing similarity search against this collection, you would be waiting an increasing amount of time to search for your match as the amount of vectors in the space continues to grow into the hundreds of thousands or millions. The workaround for this is to group your vectors into clusters called Voronoi regions, and then calculate the vector in each region that is closest to all the others, i.e. you calculate the region centroid. Then when you perform search against the cluster, you will scan the vector space by comparing against only the centroids of each region and not the individual vectors within each region. Once you find the centroid closest to your query, you then compare against all the other vectors in that region to find your closest match. This technique is called inverted file index. While inverted file index may not give you the best match, in practice it achieves a good trade-off between accuracy and speed in cases where speed is more important. Another approach for speeding up search against a large amount of vectors is to approximate the vector space by reducing or compressing the amount of dimensions of the vectors. This technique is called product quantization. If my suspicions are correct, vector search plus an indexing technique like inverted file index or product quantization is what's behind the recommendation algorithm used in production at Spotify. Please correct me if I'm wrong.